What does arctan mean? So this is just tan inverse, yeah. So it's 2 to x to the -1 of tan inverse of t dt. It tells you to use the fundamental theorem of calculus part 1. Part 1 is the portion of the fundamental theorem that tells you the derivative of an integral is the function itself. So h prime of x is going to be tan inverse of x times what? Yeah. So what is that?
Yeah, it wouldn't be
Times what? Oh, of x. Sorry, excuse me. Yes, I did not put that in there. You're right. -1 times what?
times
Negative x to the... Yep, there it is. You use the chain rule and the fundamental theorem of calculus part 1 to do that one. Absolutely. What happens if instead we had, I don't know, j of x is equal to, I don't know, x to the 1 over x of arctan of t dt? What would you need to do, Biggie? Do you remember? The fundamental theorem of oh yeah, I like the hand motion there. What do you mean by that hand motion? Split it, yeah. This is equal to the integral from x to, and you can pick any constant you want. So what constant do you pick?
0.
Pick 0 of arctan t dt plus the integral from 0 to 1 over x of arctan t dt. And then which one do you have to flip? Yeah, so then you just take this one and flip it and make it negative. And now can you apply the fundamental theorem of calculus to both of these? Yes, you absolutely can. Absolutely. When is a function concave up? Someone raised it. When is a function concave up? Yeah.
When the second derivative is positive.
Bingo. So this question is asking, when is y double prime greater than 0? That's what it's asking. Now, to find the second derivative, what are we going to need to find first? The first derivative. Can you apply the fundamental theorem of calculus part 1 to this?
Yes.
Yeah. Thomas, what's the derivative going to be?
1 over 1 plus x plus x.
Yeah, that's it. Another way to write that would be 1 plus x squared to the... So what's the second derivative, Neil? Negative. Okay, look at the board and tell me what the derivative is. To the times. Yeah, exactly. So if you simplify this, you now know that y double prime is equal to negative 1 plus 2x all over 1 plus x squared to the what power?
2.
To the 2. And we're interested in finding out where this is what? Positive. So we want to know when it's positive. So if we're looking for where it's positive, what do we need to find first?
0.
That's a noun. We need to find where it's equal to 0. Use the whole sentence. Where it's equal to 0. How do you make a fraction equal 0?
The denominator.
Not the denominator. The numerator. The denominator being 0 causes crazy weird things to happen. Space-time ends and we all get sucked into a black hole and the denominator equals 0. This time though, we need negative 1 plus 2x equal. So we know 1 plus 2x is equal to, so x is equal to. So then you know that it's equal to 0. You know that at negative a half, you know that the second y double prime is equal to, yeah, you know it's equal to 0 right there. So you need to test. You've done this before. First derivative test, second derivative test. You want to check the left and right of this to see where it's positive and where it's negative. So you're looking at this thing right here, the values here. So what's to the right of a negative a half?
0.
0. Plug in 0. The denominator is always what?
Positive.
Positive. It's always positive no matter what you plug in, right? Even when x is 0, that's still 1.
Yeah.
So you can be careful, but plug in 0, it's going to be positive between 1. And what's up here?
Negative.
Negative. So to the right, it's going to be negative. And what's a good number to plug into the left of negative a half? Plug in negative 1. This will be positive, and this will be?
Negative.
1 minus 2 is negative 1. Negative 1, it's positive, right? So it's positive over positive, which is a positive. So where is this function concave up?
Negative is smaller than negative.
To what? To what?
Negative.
Negative infinity to what? What's the other?
Negative 1/2.
Negative 1/2. Yeah, there you go. Does it include negative a half?
No.
No, it does not. You would lose a point if you included that. So it's concave up on that interval right there. Yes.
Um,
Do you remember taking a curve and then filling it with rectangles?
yes.
So you had a curve and you were trying to find this area right here. And what did you do? You broke it up into lots and lots of rectangles, right? And why did you break it up into rectangles? What's so special about rectangles? We can solve for the area of most things, but why rectangles?
They're nice and easy.
They're nice and easy, right? If I added up all of these rectangles, would they be an overestimate or an underestimate?
Right now,
Right now, overestimate. How do you make your estimate better?
make rectangles smaller.
Make more rectangles, right? So what are you doing? You're taking more and more and more and more and more and more and more rectangles. So you're not taking an infinite number of them, you're approaching an infinite number of rectangles. What happens to your estimate as you approach an infinite number of rectangles? It gets closer and closer to the actual value of that area, of the actual value. What is the area of a rectangle? How do you find the area of a rectangle? Base times height. When functions are written y equals f of x, what's the given height at a given x value? Y, or f of x, right? This is the height, correct?
Yes.
Generally speaking, in your notation, what have you referred to as the base of these infinitely skinny rectangles? Dx or delta x.
Yes.
They're basically interchangeable at this point. They do not become later, but right now they are. So you have an infinitesimally small base and a height. How many of them are you adding together? An infinite number of them. The base, does it matter? If we take an infinite number of them, could you take different bases? Could you make it wide then skinny then wide then skinny? If you're taking an infinite number of them. You can, because if you pack an infinite number of things in there, what happens eventually? They all get really, really, really small, right? So it actually doesn't matter, but does it make the math a lot easier if the bases are all the same? Yeah, it makes it a lot easier. Makes it a bunch easier. So the base stays the same. So you take the same base, delta x, delta x, delta x, delta x, delta x. What's the only thing that changes? The height. The height changes. So the Riemann Sum Notation is a way to take that and bring it all together in one notation. So maybe you've seen this right here. The limit as n goes to infinity of the sum from I equals 1 to n of, does anybody know what comes next?
F of x sub
f of x sub
I
I times what?
times delta x.
Times like delta x. You see things like this. What does this mean? What is the delta x again? What is the delta x? This is just the base. And what does the x sub I represent? The first x value and then the second x value and then the third x value all the way to the nth x value. You're taking some value and plugging it in the first one, then the second one, then the third one. And in this case, they're evenly spaced apart from whatever the left-hand limit is all the way to the right-hand limit. Infinitely close to the left-hand limit and then usually getting to the right-hand limit. This one you've probably seen, y equals x squared, going from, let's say, 0 all the way to, let's say, 1. Let's say this is y is equal to x squared. You've probably done this. We break it up. And did you make estimates with this with rectangles and you calculate rectangles, maybe you add them all together? Did you ever do that in your other class? Okay, well, could you come up with an estimate? Yeah, you could. But let's just go to the final thing here. If I break this, let's say I broke this into 1, 2, 3, 4, 5, 6. If I broke that into 6 rectangles of equal width, what's the width of each rectangle going to be?
1/6.
1/6, because you have a total distance of 1 and you've divided it into 6 pieces. But let's say we're going to break it into n pieces. If I broke that into n pieces, what's the width of each piece? 1 over n. Do you agree with that? Let's use the right hand of each of these rectangles. So the width is 1 over n. The first x value is going to be right here. That's going to be x sub 1. How far have I gone? I've gone from 0 and I've gone 1 over n. So what's that x value? 1 over n. What's this x value going to be? That's going to be x2. That's going to be equal to 2 times 1 over n. 2 over n. And what's the third one going to be equal to?
3 times 1 over n.
Exactly, 3 times 1 over n. It increments, it multiplies one more. What's the last one going to be? What's this one going to be right here?
N times n.
N times 1 over n. What's n over n?
1.
So are we where we should be?
Yeah.
Yes. So to find the area of this, what have I done? It's the width, correct? And the first height is the function evaluated at 1 over n. What's the second one? The function evaluated at 2 times 1 over n, plus all the way up to f of n over n. The base is multiplied by each of these heights. I've just factored out the base in each case. What is the function in this case? X what? We did y equals what? X squared, right? That was the function we were using. So what does this become? 1 over n squared plus 2 squared times 1 over n squared, right? Plus what? 3 squared times 1 over n squared. I'm writing it inconsistently. I'll do a better job. All the way up to what? N squared times what? 1 over, actually what? Times what? Well, it's actually just going to be n squared over n squared. I'm writing the general form so you can see the pattern. I'm writing the general form so you can see the pattern. It's actually, yes, it's 1. Thank you. What can I factor out of each of those?
1 over n squared.
1 over n squared can be do you see how they can be factored out of each of these? So if I factor that out, what's now going to be on the front? 1 over n to the what? N cubed. And what's left? 1 squared plus 2 squared plus 3 squared all the way up to? How many people have seen something like this before? So this is new. Okay, so we're going to have to spend some time on this. Here's the deal. We did this. This is the sum of squares. This is an infinite number of terms. Is there a different way to write this? Yes, there is. On page 383, it tells you that the sum of squares is equal to n times n plus 1 times 2n plus 1 all over 6. It's right there, page 383. It's right in the middle. The sum of n squares. What? So we've been looking for the area under y equals x squared from 0 to 1, and now we're down to this right here. So, and we're looking at this. This is the limit as n goes to infinity. Yay! Limit as n goes to infinity. Do that for me. Tell me what the limit is. Go. N is going to infinity. Let's look back at what we're trying to find. We're trying to find the area under the curve. Is that going to be a finite area? Yeah, it's going to be finite. It ends. It has an area, right? So it's going to have a specific value. So when we're looking at this, what's the power of the numerator? 3. What's the power of the denominator?
3.
They better be equal. If the powers aren't equal, what happens? You're either going to 0 or infinity. That would be a problem because this is finite and it exists. It's not 0. So it's a good sign. So let's get back to Riemann sums. So let's get back to that question. Let's think about this. We know what the width is. What's the function? We know what the base of each one is. It's 1 over n. But what's the function going to be? X cubed. That's all this is. That's just the Riemann sum notation for x cubed from 0 to 1. That's all it is. And is that an integral you can do pretty easily?
Yeah.
Yep. So what's that going to be? 1/4 x to the from 0 to 1. When you plug in, so you plug in 1, what do you get? 1/4. Plug in 0, what do you get? Done. You've recognized the Riemann sum as an integral, and then you've evaluated it. The recognition is hard sometimes. It is not easy sometimes. So let's look at the next one. The next one's one classic AP question is something like this. The limit, how about this? If I just gave you 1 over 50 times the square root of 1 over 50 plus the square root of 2 over 50 plus the square root of 3 over 50 all the way to the square root of 50, I'll just say the square root of 1, okay? Just make it even a little bit more general. What does that approximate? That, right there. I just picked a value for n. This right here is an approximation of this. A classic AP question is they'll give you this and say, what does it approximate? And they'll put like 1 over 50 on the outside. They'll put 1 over 50 on the inside. Does that matter at all? No, it doesn't at all. All the 1 over 50 is how many rectangles are you adding up? How many rectangles are you adding up? 50 of them. That's all it's signifying. So this is 50 subdivisions. Is it going to be decently accurate? Yeah, it's going to be decently. So for example, what would be an indefinite integral? If I just said, what's this right here would be an indefinite integral. What is the indefinite integral of that right there? No, that's the derivative. What's the indefinite? 1 over 3x cubed plus 3. This is indefinite because it's not defined. It's not fixed. But how would I turn this into a definite integral? I could say the integral from 2 to 4 of x squared dx. Now that's going to be 1/3 x cubed evaluated from 2 to 4. And that will equal a definite answer, a number. That's a definite answer, definite number. So for 22, what do you have to do first for 22? Or what should you do first? Yeah, you need to distribute. So you end up with 6v squared minus 2v plus 15v minus 5 from 0 to 4 dv. Simplify a little bit more first. 0 to 4 of 6v squared plus 13v minus 5 dv. So you end up with 2v cubed plus 13 over 2v squared minus 5v, and you're going from? Am I okay? What's nice about 0 in this case? It's 0. Yay! In this case, the 0 is 0. But this case, end up with what? 128 plus 52? Did I do that right?
I got 104.
104?
Instead of 52.
Oh, is it 16.8? Oh, it is 104. Thank you. 104. So it's going to be 128. 128 plus 84. So it's going to be what? We got 212. Woo! Are we excited about 212?